So my talk today will be about some attempts to quantify the amount of global symmetry violation in quantum gravity. And will be based on two papers. One is like already 2 years ago that I wrote with Henry Lin. And the other is on the same topic, but it's an upcoming paper that we are writing with Ibu and Huang. Now, okay, so here's the outline of my talk. I would first go through some brief review of some qualitative argument in the literature about why global symmetry must be violated in quantum gravity. Then I will talk about these two papers. I will go through the first one briefly and then maybe spend more time talking about the upcoming paper. Now, it is an old statement in quantum gravity that any global symmetry that we see at low energy, which are very important in particle physics, are either gauged or just approximate in the full theory of quantum gravity. And in this talk, I wouldn't consider the second probability from the beginning. So I will assume that the symmetry is not gauged. Then the symmetry must be approximate. And it is an unambiguous question to ask, how approximate can the global symmetry be? And the talk will be try to say something quantitative about this point. Okay? And just to make life easier, let me focus on the case of zero-form symmetry, even though it's a very interesting question, how the argument I'm presenting generalizes to higher form symmetries. And for simplicity, let me also assume that the group G is continuous. And in fact, because just to make the discussion simpler, let me just focus on the case where G is simply U1. So I can simply talk about positive charge, negative charge, rather than different representations. An important assumption I will be making is the following. I will assume that the symmetry I'm talking about is exact in the semi-classical theory. In other words, the symmetry is not broken by any field theory effects, such as higher dimensional operators or instantons. This is not an essential assumption, but it is just to highlight that the effect I will be considering in this talk are coming from non-perturbative effect in quantum gravity. Or in other words, we can think of the case I'm considering as the worst case scenario. In other words, I'm allowing the symmetry to be exact to arbitrary order in the perturbative theory and ask what is the minimal amount of violation coming from non-perturbative effect. Now, the statement that global symmetry must be violated has a very long history. And here is an incomplete list of some of the qualitative arguments made in the literature. So I think the first is, dates back to the original paper by Hawking on black hole evaporation. And there is a set of paper written by Coleman in which he argued that the wormhole effects generally violates global symmetry. And more recently, there has been a paper by Banks and Seiberg where they gathered a lot of different arguments. In particular, they made this black hole evaporation argument more precise. And more recently, there has been a paper by Harlow and Oguri where they used argument from ADS-CFT to argue that global symmetry must be violated. Yes.
What would have been seen as the loophole in Hawking's argument?
I will go through that later, yeah. So the main difference in this talk is that we want to do certain computations to quantify the violation. And let me just say a few words about why we might be interested in this question. Of course, in general, quantifying the amount of global symmetry violation is a problem that is closely related to particle physics. Let's say if we want to quantify the proton decay rate, or it's a problem that is closely related to cosmology. However, as I said, the important assumption I made is that these symmetries are not violated. The symmetries that I'm considering are not violated in the effective theory. So that is quite an impractical assumption. For example, there is no reason to assume that the proton decay wouldn't happen already given by some higher dimensional operator. So in other words, the results that I would derive in this talk are not of direct relevance to experiments. The main motivation is, in fact, to test the power of semi-classical gravity argument. In recent years, we've seen that the semi-classical gravity, in particular using a semi-classical gravity path integral, people have been able to compute various interesting quantities, including the page curve, the spectral form factor, etc. So it's interesting to push these ideas further and to see what it can teach us in more general contexts. Now let me first give you some review about the qualitative argument in the literature using black hole evaporation. In particular, it's argument given by Hawking and also in the paper by Banks and Seiberg. Now the idea is that, so here I drew a Penrose diagram of an evaporating black hole. The idea is that let's imagine that we form the black hole by throwing a lot of particles. Well, the particles have some mass m, and in total they carry some very large charge q. Okay? Now, imagine that we form a very, very heavy black hole. So a very heavy black hole would have a very, very low Hawking temperature. Now, during most of its evaporation process, the temperature of the Hawking radiation is much lower than the mass scale of the particle that we threw into the black hole. In other words, the Hawking radiation at early stage of the radiation generally will only contain very, very light particles that don't really carry charge, the charge that we form the black hole with. Of course, this is not the whole story, because when the black hole gets down to very small mass, its temperature gets higher, and at some point it will definitely be higher than the mass m. So there is a regime where the Hawking temperature is much larger than the mass m, while it's still much smaller than either the Planck scale or the string scale. So we still trust the semi-classical description. Now, in principle, in this regime, we can start to emit these charged particles because the temperature is high enough. But one particular point is that Hawking's original calculation suggests that the radiation is agnostic about whether the black hole should emit positive charge or negative charge. It will emit both signs of the charge with the same probability. So we can have both positive and negative charge emitted. And the fluctuation, the total charge, the fluctuation is incomparable to the initial charge Q. Yes?
Isn't there a second argument that doesn't rely on the positive and negative charges sort of being randomly emitted? In that, you can only start emitting these particles when the temperature is low enough.
Yes.
And so there's a fixed total number that you can emit, even if they're all positive.
Yes.
But you could emit the black hole with far greater.
With very, very, yes.
I mean, there's no limit.
Yes, I think that's
lower to start with.
exactly. I'm going to that point on the next slide.
Yeah,
yes.
That's a holography or Wittgenstein bound. Without that, you always get another Riemann.
Yes, I will talk about that. Yes. Now, I think exactly what Raphael is saying is that this slide, and Yasunori is talking about is my next slide. So imagine that the black hole waveform is very heavy. Well, maybe it's okay. Sorry, this is the previous slide. Yes, the next slide. Okay, so we haven't completed the argument yet. So the final step of the argument is more subtle, since it has to do with the final stage of the evaporation. Now, the mass of the black hole eventually gets down to roughly the Planck mass. Now, there could be different possibilities. Suppose the black hole fully evaporates to relatively light particles. Since the mass of the black hole is already very small, if it emits to light particles, there is only an upper limit of amount of particles it can emit. So it's impossible to account for all the initial charge, which is a very, very large quantity that we threw in. In other words, in this scenario, charge is simply lost in the final radiation. Now, the other possibility that has been proposed in the literature is that suppose that at this time, the final core of the black hole becomes stable. Then one runs into problem with the so-called remnants. In other words, becomes some stable particle with a mass that is roughly the Planck scale. And since we can start with different initial conditions, in particular, we can have different charge, this final remnant you would have a large family of remnants carrying different charge. Now, in the literature, this is generally viewed as a problem. For example, the argument, people might involve argument that with the entropy bound to rule out this possibility.
Do we have to wait until the black hole becomes Planckian in size, though, to say that we could generate a problem with the Bekenstein-Hawking entropy formula? Like if you just imagine some huge representations, collection of representations of some large black hole, then you would imagine you could get some huge number of microstates, right?
Right.
Of a given mass.
Right. I guess there is a question of whether you can, given a fixed energy, namely given a fixed energy, can you have an arbitrary large representation? Generally, you need the larger energy to form the larger representation. So I think to make the argument more precise, is still you need to wait until the final stage of the radiation. Of course, well, in general, there are many questions you can ask about this, and that's actually the main point of the talk, is that I feel like there are some unsatisfying features of this argument, and it can be improved. For example, it made some assumption about the final stage of the evaporation. Of course, I'm not saying that these assumptions are not reasonable, but one might wonder whether that is a necessary ingredient in this kind of arguments. And the other aspect is that you only arrive at the conclusion by comparing the initial and final state. And it's unclear at what stage in the evaporation process this violation of the global symmetry really happens. Now, the third point is that in this derivation, we assume that we form the black hole with some very, very large charge. And the argument becomes less clear if we imagine that maybe I can form the black hole with a neutral state. In that case, it's less clear how the argument goes that tells you whether in that case there is or not global symmetry violation.
Okay. What was the argument? I know that there was some, but given that Hawking's calculation is not capturing unitarity well anyway, so we must have some more subtle correction. And that correction really slightly changes baryon number versus anti-baryon if black hole is charged, like gauge charge case. Slightly gain and so on. I'm not saying that we know that's probably not the case. But what was the argument to kill that possibility or this way or that?
I think there is a...
Other than saying, okay,
right. I think there is a distinction here because charge is a macroscopic quantity that you can measure carefully. Yeah. It's different than the statement that, for example, Hawking's calculation doesn't reflect that the radiation is pure. To really verify that the state is pure, you need to do much more complicated measurement. In principle, the charge is just some local thing that I can measure with very high precision. Yeah, I think that's the argument I will give, that small corrections wouldn't really.
Yeah, you need a more drastic.
Yeah, you need a more dramatic thing.
Yeah, it wouldn't look approximately thermal.
Yeah, chemical potential.
It would have to be completely different from.
You need a chemical potential for radiation, but calculation may have missed something already. So maybe
right.
Miss the chemical potential.
So there's no way you could have like some sort of like exponentially small variation of charge the way that you have some exponentially small violation of pureness?
Probably not, because for example, if you just form the black hole by just a baryonic pattern, essentially mass and charge is the same order, so it's probably pretty big.
Yeah.
So you need to start producing massive particles at a time when the black hole has very low temperature.
I can immediately come up with that kind of argument, but I said that was a question.
Right. Okay, thanks. So, okay, very good. Now, so with Henry Lin in the paper, actually 2 years ago, we showed that you can demonstrate that the global symmetry is violated through a direct calculation without making the assumptions that I was talking about in the last page. And the situation is somewhat similar to how the development in recent years about the unitarity of the black hole evaporation. In other words, before these calculations, we already expect the black hole evaporation is unitary. But in recent discussion, we give up all these assumptions, but, well, to some degree, and did basically a direct calculation of the entropy of the Hawking radiation and see that it follows a page curve. So here, the philosophy is similar. We want to just compute some quantities in the Hawking radiation and see the answer that we get. And in fact, we essentially would be using the same tool as used in this page curve calculation. Now, okay. the setup is the following. So let me not even start with a black hole that carries a large charge. Let me just consider initial state with a 0 charge. In other words, I would choose my formula black hole with a pure state psi that is annihilated by the charge operator. So the initial state doesn't carry any charge. This is not an important point, it's just for convenient. Now, the idea is the following. We want to look at the density matrix rho r of some region very, very far away, as shown here, that contains the Hawking radiation. If the symmetry were exact, then since I start with a pure state that is annihilated by the charge operator, the global state at any time should be invariant under the symmetry. It's simply a statement that the Hamiltonian evolution preserves the symmetry. And this statement has a simple generalization to subsystems. In particularly, you can make some statement about this subsystem R. And the statement is the following.
It's a subsystem in the sense that you're looking, is R the entire Hawking radiation?
No, R is just some sub-region in Hawking radiation. It doesn't have to be the entire radiation.
Is there an advantage to looking at it? I mean, you could just look at the final product, right?
You mean I look at the radiation after the black hole fully evaporates?
Yeah.
Yeah, here the advantage is that I want to look at the radiation at different time. And this will give me, in the end, I will compute some quantity as a function of time that can give me some information about how the global symmetry violation happens over time. In principle, I could just directly look at the final state. Okay. And now, what I'm saying is that if the symmetry were exact, this would imply a certain property of the density matrix in R. So let me now denote the unitary operator generating the symmetry transformation as U of R. In other words, since I'm considering continuous symmetry is simply given by an exponential of the integral of the Noether current on region R. Okay? So it just takes that form. And if the symmetry were exact, the reduced density matrix rho R should be also invariant under the symmetry transformation. In other words, we should have a relation that is UR times rho R times UR dagger should be equal to rho R.
This is correct only at the semi-classical level, right? Because if it's a true theory with a specific microstate, then of course total charge is preserved, but you may have a fluctuation in some R and the other, depending on the state.
Now, this is, let's forget about, gravity. If you have a theory that has the global symmetry, and if the total state is invariant under the transformation, then this is a precise statement. If you look at some subregion, it has to be invariant under the symmetry transformation. In other words, you are basically saying there's some charge fluctuation in this region. That's correct. But its density matrix is block diagonal in the charge basis. In other words, rho of R.
Because your initial state is a Q.
Yeah, because initial state is a pure state. Yes. One can generalize it a little bit. Here I'm considering the simplest situation. Yeah, you can make some corresponding statement. Exactly. This can be, of course, trivially restated as the fact that the relative entropy between the transformed density matrix and the original density matrix is 0, because it's the same density matrix.
You're using the fact that you started with an uncharged state.
Yeah, here I'm using that.
It would not be difficult to.
Yeah, it wouldn't be difficult to modify the argument slightly to capture more general cases. Right? We discussed in the paper. Now, then the idea is to, let's not assume anything now. Let's simply compute this relative entropy from gravity formula and see what it gives us. And the idea is to use the gravity formula that is, well, essentially a simple generalization of the QES formula people are using to compute the entropy of the radiation region. And it's a particular formula for relative entropy that was discussed by these authors that basically tells you how to compute the relative entropy in semi-classical gravity. And if you are not familiar with this story, the main step involved in such calculation is simply to replace various quantities that shows up in this expression by the corresponding objects in the semi-classical approximation. So let me remind you that here, this rho R, this density matrix I'm writing here is supposed to be the exact density matrix. And in these calculations, one will replace the various quantities by some approximation in the semi-classical limit. In particular, if you are familiar with the recent development, before page time and after page time, one will replace this density matrix by different object in the semi-classical approximation. Before page time, you simply replace this exact density matrix by the semi-classical approximation of the density matrix on region R. But after page time, something interesting happens is that when you compute the entropy of the Hawking radiation, there is a particular island region in the black hole interior. And you are supposed to replace this density matrix by the semi-classical density matrix on not just R, but R union the region I. Okay? On the other hand, we also need to figure out what UR should become. And this is an important point, is that UR should always just go to UR, the same operator in the semi-classical description. Why is that true? Because UR, for the expert, colloquially, UR is what we call a simple operator. In other words, it can be written as a product of local operators. This can be seen from the expression of UR is an exponential of an integral of local terms. So it can be split as unitary operators acting on small subsets of the region R. Okay?
So
yes,
could
please.
You guys go back to the previous argument?
Previous slide?
Yeah.
Okay.
This is a little confusing to me because, you know, the way I would understand the RT formula, the quantum extremal surface formula, is maybe to say, okay, the entropy, the correct entropy of the unitary theory is computed as the generalized entropy
Yes.
of, you know, the entanglement wedge, which has to include the island.
Yes.
And therefore, I would have said it's the area plus the phenomenon entropy of R union I, of the state of R union I.
Yes.
But how do you get from that? I think that just was a little fast. How you get
Yeah, I didn't. Yeah, I agree. Sorry, I didn't include the calculation, but let's just remind ourselves how it works in the standard ADS CFT setup. In the entropy formula, the entropy of the boundary theory is equal to the area plus the bulk quantum field entropy. But when you compute the relative entropy, you are looking at small variation. So you have some original state rho, and you look at small variation sigma. And to the leading order in G Newton expansion, the area doesn't change. And the only thing that matters is the relative entropy of the bulk quantum field. So that's what was derived in the paper by these authors. That they argue that the relative entropy is equal to the bulk relative entropy without needing to include the area contribution.
Yeah.
Okay. And, okay, right. Here I was saying, right. Here I was arguing that UR just goes to UR because it's a simple operator. And now, of course, this property was also utilized in some other arguments by Harlow and Uguri and Harrow and Shekolian. One should perhaps contrast the situation here, this UR operator, which is a very simple operator. It's just integral of charge operator, from some other discussions in the literature of complicated operators that you can act on the Hawking radiation. And those operators are conjectured to be able to manipulate the information in the island. Here is not, it's different from that situation. Okay, now after all the setup, we are able to compute this quantity. And before the page time, after I replace all these quantities, tells us that the relative entropy in the exact theory can be computed in the semi-classical approximation as the relative entropy of the density matrix in the semi-classical approximation after some unitary transformation with itself. Now, since in the semi-classical theory, the density matrix is indeed invariant, because I assumed from the beginning that the symmetry is exact in the semi-classical theory, this relative entropy is exactly 0. This is what happens before the page time.
Is this the only place where that assumption matters?
Yes, this is the only place where that assumption matters.
Couldn't you have argued that it'll be true anyway, just because it's a thermal state, and so you're as likely to? I mean, don't the various charged states have to have equal probability?
Well, if the symmetry is already broken at the perturbivity level, the statement that the Hawking radiation is a thermal state wouldn't immediately imply that you should have the same probability of positive charge and negative charge, right? You can favor one or the other because charge doesn't commute with Hamiltonian, etc. Now, after the, Michelle, do you have a question? No? Okay. After the page time, we do the same thing, we do the replacement, but importantly, we need to now take into account of the existence of the island. And now, important observation here is that since the semi-classical density matrix, now we have a density matrix on the union of the two regions, R union I, it is not invariant under UR. It is only invariant under the combined transformation, that is the product of UR and UI. In other words, you also need to act with a unitary transformation here in order to preserve the density matrix. So this density matrix is not invariant under the transformation. That means that you get a non-zero relative entropy.
Why define your global symmetry, not UR, UI, but it's UR? Because it's a global.
Because as an observer living in the radiation here, the only meaningful statement that I can say is that I want to test whether my density matrix is invariant under my symmetry transformation operator or not.
That sounds like you can also define under UR, UI because you cannot measure I part anyway, so you can have some
well, but yeah, you can define another operator. I agree with you perfectly that in principle I can define some unitary operator on R that preserves my state. But that operator wouldn't be the operator that I wrote down from the beginning. That is an integral of the charge.
In fundamental description, it is not the simple operator in fundamental description, but it's a simple operator in a sense of semi-classical.
No, I don't think it should be. I don't think it would be a simple operator in the semi-classical description anymore. Because if you write this UI operator in terms of operators in the radiation, it should be some fairly complicated operator, based on the idea of integument wedge reconstruction. If you want to reconstruct this UI operator using operators in the radiation, it should be some.
In the fundamental degrees of freedom, say, on fundamental
yes,
degrees
yes,
of freedom is complicated.
yes.
But if you use that argument, I kind of understand. So I'm just saying you may be using more than what you said.
Maybe I'm confused about. What do you mean by an operator is in the fundamental or the semi-classical?
No, okay.
Yeah.
For example, if you just already extract some complicated interior degrees of freedom and write it as a semi-classical spacetime, that's effective theory. And usually we could say what we usually call global symmetry is a global symmetry, like a splitting phenomenon in the effective theory only or something. You have to probably appropriately define. In that case, it sounds like you are UI.
Right.
Then why that's not the case? That's
right.
I'm sympathetic.
Let me fully understand. I think your proposal is that basically I can define some other operator that is the simple operator that I wrote down, UR times some other thing, right? But one problem of that is, well, first of all, that's not usually what people mean by a global symmetry as what a low energy observer would mean by a global symmetry. Usually we mean something very specific. It's just the operator that I wrote down earlier, this operator that I wrote down, okay? That's my definition of the global symmetry transformation. The other problem with your proposal is that this operator.
So I'm just saying why you do this on nice slice, which go through R and I.
Which goes. I'm defining an operator, the symmetry transformation operator in the region R. I'm not sure why I should.
Can I ask a question?
Include.
But isn't what you're right? So then, you know, the way that the state is produced, you probably have some baryons entangled with antibaryons in the island, and now you rotate the baryons to antibaryons in the region R. That's changed the global state because now it's antibaryons to antibaryons, and I think that's just clearly a change. Like, but what else were you going to interpret your R to be?
So usually global symmetry means you do the symmetry on whole causes, right? So otherwise, of course, you can be changed. Oh. So here you take a whole causes rest to be just R.
No, here I'm making some statement about the symmetry transformation in a sub-region in space-time. I think that's a meaningful statement to make. I don't really have to talk about the unitary transformation on the entire slide.
If that was necessary, then it would be a meaningless thing for physics, right? A global symmetry, because we never.
Yeah, I can talk. We can talk about some meaningful statement about whether a subsystem is invariant under symmetry transformation or not. And that's usually what we can really test in experiment. Yes?
I guess, maybe this is what Yasunori is getting at, maybe I'm just rephrasing it, but I guess what I'm worried about is what you're describing here is a global symmetry, a unitary operator in the fundamental theory. But if I then go to the semi-classical approximation, how do I know that there won't be some other operator which looks like UI, UR, but that operator is actually the semi-classical approximation to this operator?
Of course, I know probably that's not the case. This is not my
situation. I don't think this is actually what happened.
Because, for example, if you have a state, so clearly you can have a baryon approximative universe, you have baryon here, you have antibaryon here, you just do the rotation only in this subregion, and of course it's not invariant because you have only baryons, right? So
if you have an entangled state so you have a Q, let's say Q left minus Q right, right? That's the state you are imagining. So let's say the total state is some vacuum, which maybe includes a sum of terms like these.
Yeah, this is a particular case. Some arbitrary state, then that's not true, right?
Arbitrary state is not true, but even in this case, it would be invariant under the local symmetry transformation. Because if you really look at it carefully, after you're tracing out the R system, let's say, the density matrix on the left will be a block diagonal density matrix that looks like Q left, Q left. Okay? And when you act with the unitary, which is e to the I alpha Q, on the...
I'm thinking about the state, which is not the sum. It's just the Q left and minus Q R.
Okay, not the sum.
Yeah, that's not the vacuum, but it's anyway, that's state.
Yeah, then the density matrix would just be Q left, right?
And then that's not invariant.
That is invariant, because if you act with U on the left and U on the right, you get e to the I alpha Q times from the left, and row left, and e to the minus I alpha Q on the right. So these two phases just cancels out. Maybe that's where the confusion comes from. In this, it is invariant, even though there is charge fluctuation.
Even if you have a charge asymmetry.
Yeah, it is invariant. I think this is probably where the confusion is. But here, here we are making a stronger statement that it won't be invariant. That really signals that the global symmetry is violated.
Okay, so simply the absence of open element is already enough to say that.
Yeah, we are not making trivial statement like there is no charge fluctuation. That's certainly not true. Right. Okay. Okay. Now let me get back to the main point. Is that the violation of the global symmetry is captured by this quantity being non-zero. And it is a quantity that can be computed directly in the semi-classical theory. We demonstrated such a calculation in the case of JT gravity coupled to Dirac fermions, where the symmetry being U1. And in that case, you can do this calculation explicitly. And what you find is a curve like this, that before the page time is this quantity is just 0, well, after the page time, it jumps to some non-zero and order 1 in G Newton amount and increases with time. Okay. Now, one particular point I want to highlight is that the effect of the violation is already visible at the page time, as long as you are able to collect all the Hawking radiation and compute this quantity. Now, the late time assumptions in the previous arguments are not necessary. Of course, it would be interesting to see how it connects with those arguments, but I won't go into that here.
This is G Newton to the 0th power because you're looking at fluctuation.
Yeah, because here it's just some field theory calculation. Yes, not a very large entropy.
So if you allow a charged initial state, Hawking's argument, for example, would say that the effect you would expect violation to be visible earlier, right?
Yeah. So if you have some charge already in the initial state, then I think the statement is that this wouldn't start with 0, but it will still have some jump at the page time. Actually, that's what I'm going to talk about in the, well, a slightly different version that I'm talking about is here. It is if the symmetry is already violated at the perturbivity level, then one can ask, is there still a meaningful signature of the non-perturbivity effect? And the answer is yes, because if it is already violated at the perturbivity level, this curve will already start to grow before the page time. But still, this effect of including the island will still give you a discontinuity in the curve, which signals a jump at the page time. And so here you see there is a clear separation between the two effects, and that you can see from in this quantity.
But even if the initial state is charged, if there's no perturbivity violation, it's still broke up, right?
Yeah, in that case, it's true. Yes.
Because it's the same argument. I mean, even if it's charged and so on, no auxiliary element, it's just one.
Yeah, I don't remember how it depends on time. That I have to think slightly more about. But it will certainly be non-zero.
So it's like
Right. I think in that case, I don't exactly remember the argument, but in that case, if you have start with some non-zero charge, I don't remember whether it grows.
Was that 0? You said it's 0 always. Because it's a broke diagonal. I mean,
yeah, here is 0.
It's 0, right?
If it's non-zero total charge, in this this case doesn't matter.
So it's group still.
Yeah, maybe let me get back to you on that point later.
Sounds like
well,
it doesn't matter to prove your argument.
Here I'm dividing the entire system just in two subsystems. Maybe it's more complicated if you have multiple subsystems. Let me get back to you on that point later. In any case, we did consider that situation in our paper. I just don't remember the conclusion now.
Is there an interpolation here? Is this, for the page curve, naively,
right.
You have a sharp kink, and here you can have
right. Here, in principle, one we imagine that after you do sum over all these different saddle points, you get a smooth curve rather than a discontinuity. Okay. Now you can ask, well, you're just playing trick here, just replacing this quantity by by the island, and where is really the gravity effect? Now the gravity effect is of course hidden behind the island. It's really when you derive these formulas, the gravity effect becomes important. And here the point is that the replica wormhole serves as an explicit realization of Coleman's wormhole. So we had more discussion on this aspect in our paper. And in particular, there is another paper by Poshen, Luca, and Zhenbing at similar time, where they also discuss similar effects.
Here you imagine computing the relative Renyi entropy and using the relative.
Yeah, you can imagine compute something like that. Yeah, second Renyi entropy, then there will be some wormhole in the middle. And
for the ordinary Renyi entropies, that's what you would do to compute the page curve, right? But here you're trying to compute some relative entropy.
Yeah, you will replace some of the density matrices by this transform density matrix. And in that case, if you really think about that calculation, the charges, the only reason that charge is lost is because charge flow through those replica wormholes. between different copies. Okay. Now in the second part of my talk, let me talk about the other thing that we are doing right now. And the idea is that in the previous paper, even though we were able to compute some quantities that are sensitive to the global symmetry violation, these quantities involve very complicated relative entropies. And they are not very transparent. They are definitely not the standard thing we used in particle physics. And they are also quite restricted to a particular background of, let's say, evaporating black hole. Now, one would hope to have some simpler characterization of global symmetry violation using simpler quantities. One obvious such candidate to consider is just 2-to-2 scattering amplitude in flat space. So you send in some two particles with some charge and see what's the amplitude that some particles with different charge that comes out. But this is, in general, very hard to compute. And recently, we consider as even simpler setup compared to these. The setup that we considered is a problem which involves scattering amplitude of thin shells in ADS space. Now, the setup is the following. Let's look at ADS space, and imagine we send in a thin shell with some global charge A, and ask what's the probability of the shell with some different global charge B that comes out. Now, we mainly consider this process in ADS because in that case, the boundary conditions are easier to specify. We simply insert some local operators along the boundary of ADS space that would create such a shell. We have some ideas on flat space limit, but currently we are not entirely satisfied with the picture yet. So let me now focus on the ADS case. Now, of course, since here I'm imagining sending in a spherical symmetric shell, you can do a dimensional reduction and reduce the entire thing to a two-dimensional picture. This will, in general, be a two-dimensional dilatant gravity with general dilatant potential. And I'm sending in some particle from infinity and ask what's the probability of a different shell that comes out.
How to prepare global symmetry in the bulk?
Sorry, can you ask?
How to prepare global symmetry in the bulk?
How to prepare, well, I'm assuming that the bulk theory has certain global symmetry. That's the starting point. The effective field theory has some global symmetry. Let's say you have some U1 symmetry in the bulk, some charged fermions, without gauge field, of course.
And is it possible to have that?
You mean, your question is whether it's possible coming from some string theory construction? Yeah, that's a more difficult question. Maybe Tom is an expert to answer.
No, right? I mean,
Yeah. Well, you might imagine, yeah, maybe go ahead, sorry.
So, I mean, at the point of your talk is you're not supposed to have an exact global symmetry, so there should be some operator somehow violating it.
Yeah, but you could imagine with some complicated construction, you can have some approximate global symmetry. Then the question that we're asking is how to quantify, how to put a lower bound on the violation.
You can extrapolate that piece.
I thought what you were doing was a sort of argument by contradiction, that you would start out by assuming that the quantum field theory in the bulk has an
Yes.
exact global symmetry, and you do some calculation that includes gravity
Right.
to show that that's just inconsistent.
Yeah, but I think maybe Yasunori is asking maybe more about whether it's even possible to construct a quantum field theory that preserves the global symmetry.
It doesn't matter. It
Yeah.
doesn't matter.
Yeah, yeah.
Even if that's the case.
Even if that's the case, yes. Now, let me denote this amplitude as A to B with energy E. So we really want to fix the energy of the intermediate state. Since the symmetry, now we're assuming that the symmetry is exactly in the semi-classical theory, this amplitude is simply 0 if you naively evaluate it, which just means that it's equals to 0 plus some non-perturbatively suppressed amount. Now, the idea that we're following is, of course, conceptually not new. It's entirely based on earlier paper by Pennington, Schenker, Stanford, Young, and also another paper by Stanford. The other is that the idea is that instead we would choose to compute the square of the amplitude with suitable average. In other words, we look at the square of this quantity with some average. Now, one might ask, what is the average here? one can think of the average as an ensemble average if the theory is dual to an ensemble. But perhaps more naturally here, one could simply interpret it as averaging over some high energy window. In other words, we do some very small smearing on the center of mass energy E and compute the average. And as was discussed in these papers, the calculation of the square involves 2 copies of the space-time. So here I'm drawing 2 copies. And there could be a configuration where in the middle, the 2 space-time are connected by some wormhole, and the particle A simply goes through the wormhole and end up at the A dagger at the other copy, and similarly for the particle B. So this diagram would naively just give you a non-zero contribution to the square. The conceptual work is already done in the literature. What we did is simply to try to understand the property of the geometry better. And in fact, what we found is that the solution has some exotic features that we didn't expect beforehand. Now, let me just tell you a little bit about what these features are. Now, how do we really construct such solutions in gravity? We can take a few steps. Now, step 1 is to look at some solution with simply just one shell and keep the energy to be general. So here, E and E prime, I didn't say it, but I'm denoting the E prime as the energy before I insert the particle. So in the end, I want to look at this case where E prime is equal to 0 because I want to insert the particle in the vacuum. But in the construction, let me keep it general. And E is the intermediate energy, the energy after I insert the particle. Okay. Now, in the one-shell problem, let me keep E and E prime general. And the quantity I will be computing is the following quantity. So I want to insert operator A, insert the shell A, and ask what's the probability of the shell A dagger that comes out. And I'm projecting the intermediate. So this P is some projection operator that projects the energy to be E prime before I insert A and E after I insert A. Okay? Now, if you look at the calculation of this quantity, in general, the saddle point geometries are given, there are 2 distinct situations. If the energy E is smaller than E prime, so maybe let me explain better. In this diagram, each part of the geometry is given by some ADS-Schwarzschild black hole solution. And you are patching different solutions with different energy along the thin shell. So it's some standard thin shell solution that are discussed. Well, earliest is by Israel and also by some recent paper by Hartman and collaborator. Okay? And when the energy E is smaller than E prime, the solution with energy E covers most part of the geometry. And the solution with higher energy just covers very, very small portion of the geometry. In particularly, in the solution, there is just one fixed point, one bifurcation surface, and it is associated with the lower energy E. In the other situation that we're already interested in, E greater than E prime, we simply exchange the definition of the energy, and it looks like the following. So the solution with E prime covers most part of the geometry, and the solution with E covers very small part. Okay. Now the second step to construct the wormhole is to cut and glue various pieces of the geometry together. And let me first look at the simpler case, which is E smaller than E prime. That is not the final case we're interested in, but it's simpler. In this case, I had a one-shell solution like this, and I can cut the solution open along the reflection point, along a reflection trajectory of A and A prime, A and A dagger along this dashed line here. And I can join it to another piece that is associated with the shell B and B dagger. Okay? So after I cut and glue, I get a wormhole geometry like this. So it's a geometry where I have A and B on one side and A dagger and B dagger on the other side, and it has a fixed point that has energy E.
Spatial wormhole, right? It's not.
here, maybe I should put the wormhole in a quotation mark because it's not really, it doesn't really have two asymptotic boundaries. But if you cut the solution open here and here, then it will be I think, well, because this is Euclidean time direction, I would still maybe call it the space-time wormhole.
To do math in an equal time series. T equals 0 slice, you have wormhole, but it's not space-time wormhole.
No, well, so here in the diagram, this direction is the time direction. Yes. It's the Euclidean time direction. Maybe that's what you if you look at the slides like this, if you mean, okay. Yeah. And I think to really think of it as a wormhole, this will be the cross-section of the wormhole. Maybe let me draw it better. Yeah, the topology here is just a disk. So maybe let me not talk about wormhole here. I will have a real wormhole later. But maybe let me delete that word. Okay, get a geometry, and its action here is given by the entropy of the fixed point that has energy E. So it goes like, if you look at the action, this contribution goes like E to the S plus some small correction of order the rest mass of the shell. Okay, so later on, I would not keep track of these small corrections, but it can be worked out explicitly. Now, the main thing I want to highlight here is that once you go to the other situation where E is greater than E prime, you see a puzzle with a cut and glue prescription, because in the previous slide, I was cutting this solution with E open here at the reflection point, but here, it seems that I can't cut anymore because there's not enough space to cut. So does this just imply that the solution doesn't exist in the situation that we're already interested in? Okay. Now, a point is that there is actually a formal analytic continuation of the solution to the regime. So initially, you start with E small, and then you can analytically continue the solution to the region where E is large, and we can see what you get. This is the solution that we constructed earlier, and it has the property that the operator A and operator B are separated in the Euclidean time direction by some positive amount. And this positive amount is in general some function of the energy E and E prime. Now we can ask what happens once you continue E to be greater than E prime. When you start to increase the energy E, you see what happens is that A start to move rightwards and B start to move leftwards. And at some particular point, they cross each other. And if you do this calculation, you see that when E is greater than E prime, we actually find that this tau becomes negative. In other words, the naive geometry would look like the following. You still have this large piece associated with the solution with E prime and also this piece with E prime. But the middle of the geometry would be this yellow thing that I draw here that includes a negative Euclidean evolution. In other words, I evolve forward in Euclidean time here, and then I evolve backward in Euclidean time through this region and reach the operator B. Okay? And it's negative simply coming from the analytic continuation that I made in the last slide. I hope I explained this geometry somewhat clearly, because I think it's a bit confusing how it arises. In any case, in this geometry, we are identifying this shell with this boundary of the middle geometry and this shell with the other boundary. Okay? And this negative Euclidean evolution has an interesting result, is that the contribution to the action from this fixed point comes with a minus sign. So if you look at the action of this geometry, it goes like e to the 2s e prime, which comes from these two fixed points, minus s of e. In particular, if you take the limit now, take the limit that e prime goes to 0, you end up with a solution that has two empty ADS spaces on both sides and a black hole solution, but with negative Euclidean evolution in the middle. And the action of this solution, the total contribution of this solution is simply e to the minus s. Well, S is the entropy of the black hole with energy E. Now, of course, there's many questions about this negative Euclidean evolution. It's a very weird concept. But let's first state the result that one of the results that we find is that the amplitude squared is exponentially suppressed by the entropy of the black hole. It goes like e to the minus s, which is probably the most naive answer one can write down. But here we see how it arises explicitly from the geometry. But of course, one should ask these questions, does it make sense to consider negative Euclidean evolution? It's really exotic. Let me make a few comments. The first comment is that it is essential in getting the expected answer, in getting this minus sign. It seems to be important to get that sign to have negative Euclidean evolution. The second comment is that it actually has a simple origin. Notice that the final amplitude as a function of the energy is exponentially suppressed towards large energy. So if we just set up this problem, the gravity would prefer to have smaller energy in order to make the action smaller or make the whole contribution larger. So in order to stabilize the energy and consider the process as some particular energy E, we need to add to it some negative Euclidean evolution in order to increase the contribution, enhance the contribution at high energy, and stabilize it. Now, another comment is that inserting some factor that look like e to the beta h is especially bad if you think of the canonical example. But here, we are fixing the energy, so perhaps it's less severe. The problem is less severe.
So this factor is pretty much a form factor for black hole.
Can you say that?
Form factor
Yes.
for black hole production.
Yes. Another comment is that one can verify that this calculation matches with the exact answer in JT gravity. So you can see in JT gravity, this is the correct saddle point. However, there are also some problems with the negative Euclidean evolution. For one thing, it is really hard to reconcile this negative Euclidean evolution with the Lorentzian picture that we started with. We want to look at some process where a shell A comes in and a shell B comes out, and there should be some Lorentzian time involved in between. How could it be that this process involves a negative Euclidean time separation between the shells? And another problem that is perhaps not surprising is that if you study quantum fluctuations around such a background with negative Euclidean evolution, you see that the fluctuations are not suppressed. So let me make a simple physical argument why that is the case. Let's imagine a process where before the shell A really falls to the center, it emits some particle chi that stays at some large radius. And then it gets absorbed by the shell B before it fully comes out to the boundary. We can ask, how does this process compare to the solution that we had? And since the shell A emitted a particle chi, the black hole in the middle would have a smaller energy. Let me denote that by E theta that is smaller than the original energy E, since it emitted the particle. Which means that this new process actually is enhanced compared to the original solution. This is simply because the final amplitude is exponentially suppressed in the entropy. So if the energy is smaller, the entropy of the black hole is smaller, this new contribution is actually much greater than the original contribution that we were looking at. This is a simple way to see that in general, the quantum fluctuations around such a background is not under control. So maybe in the last few minutes, 5 minutes, let me just tell you about an improvement on the construction that solves the problem. And this is one main point of the discussion that we are working on. So it turns out that in this naive construction that I talked about, we are missing an important ingredient. The geometry I showed you in the middle actually classically has a zero mode, which is a zero mode that rotates one of the shell relative to the other shell. Okay? So you can, since there is a fixed point in the geometry, you can rotate them relative to each other. And this means that in the final solution, we are free to insert some large amount of Lorentzian evolution between the particle A and B. In other words, I can insert some amount of Lorentzian evolution, IT, so here is Euclidean time, so I insert some IT here in the bottom, and insert an opposite amount minus IT in the top. That would still be a classical solution of the problem, the classical settle point of the setup. Why would this be an improvement? Let me give you just one very simple intuitive argument. Why does this solve the problem? First of all, it solves the puzzle that A and B are just separated by some Euclidean time. Now we solve this by hand by just inserting some large Lorentzian time in the middle. But secondly, it solves the problem with unbounded fluctuation, because if you separate the operators by some very large Lorentzian time, the particle that this shell A emitted, this chi particle, will fall back into the horizon after some time. So after it falls back into the horizon, the black hole would come back to have energy E rather than E tilde. In this diagram, I'm drawing the case where the chi particle stays at large radius. And the probability for particles to stay at large distance is suppressed exponentially at late time, which is precisely controlled by the quasi-normal mole frequencies associated with such the wave packet of this particle. In particular, if you look at the quasi-normal mole frequencies, the frequency will have some imaginary part, and the contribution from this diagram would decay at long time as exponential minus the imaginary part times t. In other words, if you added some large Lorentzian time, the fluctuations, all these diagrams with extra particles outside the horizon will be suppressed compared to the original solution at long time. So at a very long time, the original solution will be the dominant contribution. And one way to draw the geometry is the following. So remember that in the earlier picture, I'm inserting some Lorentzian time here in the bottom and at the top. So you can think of cutting this wormhole open and join these two slides into two slices on the thermal field double state, okay, which are separated by some very, very large Lorentzian time evolution in between. And this middle part of the geometry is somewhat analogous to the so-called double cone geometry that has been discussed by Sa, Schenker, and Stanford in the discussion of spectral form factor. This might be a bit more technical, but there are some comments that we are working on discussing the relation of this geometry with the double cone and certain aspects of that. I won't have time to talk about that. Okay. Let me just make some further comments about this solution, and then I'll conclude. So there might be some very long-lived quasi-normal modes, such as modes that carry very large angular momentum. So you can imagine this shell as if forcing emits some particle with large angular momentum that stays very, very far away, and it decays very slowly. Of course, the probability of emitting such modes are suppressed. So it's a non-trivial exercise to try to see whether really at some fixed time all the possible perturbations are suppressed. Ideally, we would like to consider the flat space limit of this solution. Now, naively, the flat space limit seems straightforward in the sense that the final answer that we get from the geometry separates into two pieces. One is the universal piece, namely minus the entropy that simply associates with the energy of the intermediate black hole, and the other piece that I didn't even write down, which is of order of the rest mass of the shell, that has to do with the detail of how you inserted it near infinity. So the flat space limit would only affect this piece, which a priori is universal, no matter whether you consider charge violating process or considering some other scattering process. And the real universal piece of charge violating process comes from this entropy suppression. However, one point that we are not satisfied with is that one would have hoped to have a more intrinsically Lorentzian construction rather than relying on these Euclidean structural black hole solutions, this thin shell construction. Okay. So that's a point that we are still thinking about. Relatedly, we are considering a situation that is not very realistic in the sense that the environment outside the black hole is in thermal equilibrium with the black hole. This is simply the fact that we are looking at these Euclidean diagrams. If you slice it open, it's some thermal field double state or Harder-Hawking state. So the environment is in thermal equilibrium with the black hole. In a real scattering situation, you will imagine that only very close to the black hole you reach some thermal equilibrium, but very far away you should have 0 temperature. Okay? So in this case, we would expect there's further suppression to the charge violating process coming from this particular aspect. And exactly how to quantify that is also another question we are considering. Okay. Now let me conclude. So in this talk, I discussed 2 different ways to quantify global symmetry violation. There is a more abstract way of using quantum information quantity. Calculation is much simpler, but it's more restrictive, and the quantity is not so transparent. There's a different way of just simply using wormholes to construct these charge violating amplitudes. The quantity we are looking at is very simple, but the final construction involves some exotic features. In both cases, the calculation really uses semi-classical gravity path integral, and in particular, they involve wormhole effects. Wormhole plays an important role in both cases. Now, it would be interesting to see whether similar methods can be generalized to other contexts, such as higher form symmetry or even weak gravity conjecture. So in particularly, there is an interesting paper by Alexei and Amir in 2021 on this subject. But I think there are probably more to say on that particular point. Now, the final thing is that it would be interesting also to understand in this scattering discussion whether one can use this high energy behavior of the amplitude to constrain low energy, perhaps along the line of using the dispersion relations that played an important role in the recent discussion of S-matrix bootstrap, etc. So I think that's all I have. Thank you very much.
Question for Yiming.
Yes.
In your first calculation, it seems that the violation is power suppressed by Berkeley entropy. It's
in a second.
To the G Newton to the 0.
Oh yeah. Right.
So it's like power suppressed. Here it's exponentially suppressed. Is it possible because you're looking at just the exclusive process, like A to G?
Yes. Very good.
And
Yeah.
you have A to the S kind of the final state, so it eventually goes to power suppressed.
Yes. Very good. So. Yeah, exactly. So here we are looking at exclusive amplitude, so we fix the initial state and final state. So we're looking at some specific matrix element, estimate what that is. In the entropy calculation, in principle, we are summing over exponentially many matrix elements. So somehow they add up and give you order 1.
Your calculation, the initial one is more kind of precise in a sense that here it's e to the minus s, final state e to the s. You don't know after that what happens to power. You computed that power is 1 by s in the first calculation.
I see.
Is it fair to say that?
Maybe I didn't understand the statement about 1 over s.
Because it's a G Newton to the 0.
Right. Okay, I see what you mean. Okay.
So
right. Yeah, some quantum field entropy, exactly. Yeah,
I'm assuming that even if it's initially charged, it's the same.
I agree. It's really amazing that this entropy formula can somehow produce these interesting quantities, which is, I don't know, well, maybe there are some more general lessons to that, but it's really amazing that you are able to compute this whole entropy even though you can't compute each matrix element accurately. You can only do an estimation like this. Yeah, I agree. It's an interesting comment.
That it's only power suppressed, right?
Yeah, it makes sense. It makes sense. It's not exponential. It makes sense. Yes.
First of all, very nice talk. And I guess another comment is in this summary of things that would be interesting to do. I mean, I think what would really be nice is if there's some violation of global symmetries that doesn't just come from, say, pure gravity that we can calculate there.
Yeah, I think that's what I'm trying to say here. Yeah.
I think it's,
Yeah, there is some difficulty. Let me just mention that there is some difficulty of using these dispersion relations. Essentially, in all those things, well, first of all, I'm not an expert, but at least I think generally you would require certain knowledge about the amplitude. So here S is the Mandelstam variable in the analytic property in the upper half plane. But here, generally from these black hole arguments, you conclude that the entropy goes like e to the minus s. So here S is the entropy. Oh, you can see it? Okay. Well, here you conclude that the amplitude goes like e to the minus s. Now S is the black hole entropy. So if you translate in 4 dimensions, entropy goes like energy square. So it goes like little s square. And that tells you that essentially,
Energy squared is little s.
sorry, little s is the center of mass energy. Maybe that's how I defined it.
Usually
Okay.
Mandelstam variable different.
Sorry. Okay.
It's okay.
That's embarrassing, but okay. Well, the only thing I'm really trying to say is that it wouldn't be you wouldn't be able to trust this expression on the entire upper half plane, because at some point this becomes exponentially large and it becomes the calculation breaks down. Right. Sorry. Yeah. S is energy square. Yeah.
P1 plus P2 whole square.
Yes. This is recorded. That's that's really embarrassing. Okay.
Other questions? If not, let's thank you again.
Okay. Thank you very much.